All right, welcome back to Calc 2. Today we're going to start talking about multivariate functions. Okay, don't let the name scare you. Okay, we have multivariate functions, and it just means like there's an x and a y. Okay, you actually have some experience with these before. You may not realize it, but if you've dealt with ideal gas law, right? We have PV and T being our variables. So something like P is equal to nRT over V. We could rewrite this as F of TV is equal to nRT over V. That would be the math way of writing it. But we can vary both temperature and volume here. Okay, N and R I think are usually constants. And then go through, or at least they're set. I mean, I know R is a constant, and I think it's a set. You can go through and do that, but you've done this before. Okay, now we're going to make it, dress it up in fancier clothes and have us do this. But anytime you have like an equation where you have more than one variable, it's a multivariable function. Okay, and I know most of you have had at least this much chemistry. All right, so just to start a little bit. Okay, we're not going to go through the whole thing here. But we have f of xy is equal to 8x minus 5y plus 3. So one more thing before we get into that. F of xy equals 8x, what was it? 8x minus 5y plus 3. So coordinate system. We use what we call a right-handed coordinate system. That means if we put our hand on the x-axis, okay, and like curl it into the y-axis, your thumb should be pointing in the direction of the z-axis. Okay, so x kind of curled into y will tell you the direction of z. All right, and that's called a right-handed coordinate system. Okay, now you don't have to use a right-handed system, but generally you're going to tell people like why you chose to use a left-handed coordinate system. There's nothing wrong with any of those choices. If you wanted to do x and y like this, x and y, you would put your hand on the x, curl it to the y, and your z is going to be coming out of the board, coming out of the wall. Okay, so that's generally how you want to think about this, and then we just rotate it, right? So we just rotate the z into that, and that's how we have our x and our y coming the other way. Okay, so that's our x. Trying to put my hand like for x and curl my fingers into y, we get our thing going up. So this is where the rule of like righty tighty lefty loosey comes, right? If I'm going to curl in a light bulb, we're going to twist the light bulb. You're going to right hand roll it, and the light bulb is going to go into the socket. Or if you want to undo it, right? So we're going to twist it the other way. We're pointing down, and the light bulb is going to come out of the socket. All right, so that's, again, the convention is we use a right-handed rule, but you don't have to. Okay, if you really want to use something else, please. But usually some people are going to ask you like, why didn't you use a right-handed coordinate system? Why did you make things confusing for everybody? So you would want to tell people what you're doing with that. Okay, so if you have a system where y curled into x makes it go up, that might be a thing. Like maybe you're dealing with all like left-handed sugars or something. It would make sense to use a right-handed or left-handed coordinate system in that case. So there's our thing. All right. So yeah, we just plug these values in. We say f of 3, -1. Okay, so we want f of 3, -1. We're just going to plug in. Well, the 3 is the x, so we have 8 times 3 minus 5 times -1 plus 3. So that's 24 plus 5 plus 8. I'm sorry, plus 3. Go ahead and add those up. So this is 24 plus 8 is equal to 32, and there's our spot. So not so bad for at least the first little bits of this. They're just having you plug in, get used to the idea of multiple variable things. Okay, so I'm going to go to the next part of this thing. because I think you guys are going to be okay with all of this. Yes, let's just go. Okay, that's fine. All right. Okay. Now, next one is graphing. We have to graph a plane. All right. Now, I think your homework has some harder things on here. I've never really asked the harder questions because I think they're kind of neat, but they're really hard to draw, and it's not something that I want to subject you to. So we'll go ahead and do that. So here we have 5x plus 4z is equal to 20. Okay, 5y rather. 5y plus 4z is equal to 20. Remember, in an xy coordinate system, right, or xy coordinate system, if you just had like y equals 3, what kind of a line was that? Right, that was just a horizontal line. And we had xy coordinate system. You had like x equals 1. What kind of a line was that? Right, that was just a vertical line. All right. So sometimes you're going to have all three variables represented, and when you did that, right, you had like, you know, your x was your line was spanning both x and y values. But when you just had y, like you didn't really span y values. It was just the one. You didn't really span x values. It was just the one. Okay. Same thing was going on here. So here we're going to have a plane that's going to intersect two of the planes, two of the axes, but not anything else. Okay, so what we're going to do is we're going to use something called method of intercepts. Okay. Very powerful technique. We set all but one variable to 0. Okay, and then solve for the other one and plot that point. Okay, plot remaining point. Okay, and then we just take turns. We take another variable, we set everything else but that variable equal to 0. Okay, then move to another variable. And repeat. Okay, and just keep going with that. Okay, I think there's a double bar. I'm not sure. It's been a while. So how do we graph this? 5y plus 4z is equal to 20. Well, let's draw our coordinate system. So we have, here's our x, here's our z, here's our y. Okay, so we have our 5y plus 4z is equal to 20. Well, let's set, it doesn't matter which one you pick first, let's set z is equal to 0. So we have 5y is equal to 20, y must be 4. So we got 1, 2, 3, 4 on the y part. What's x at this point? Well, we don't really care, but x would be 0. Okay, so we're just going to have that point there. Okay, z is 0 because we're not going anywhere here. We're not going anywhere in this direction. So z is 0, and we went 4 points, four steps in the y direction. Okay, and then we're going to set y equals 0. So we have 4z is equal to 20. Well, they come up with some really nice ones here, don't they? And then z is equal to 20 over 4, which is 5. 1, 2, 3, 4, 5. Notice we're not going anywhere in the z direction or the y direction. We're not going anywhere in the x direction. We just went 5 in the z direction. And then we go ahead and connect this dot. Okay. So in the YZ coordinate system, this would look like a line, but in the XYZ, right, we're going to have, this is going to go forward because X doesn't, we don't really see X. Okay, and back and back. So it's kind of like you leaned a plank up against a wall. Okay, that's what this is going to look like. Now it's a plane, so it goes infinite, and this direction, this direction, this direction, this direction. Okay, so it's a plane, but the silhouette of this thing, or the tiny little bit of this, is you lean a plank up against a wall. That's what this looks like. Okay, so that's what we've got. Let's see here. See, this is the kind of thing I want to look at right here. Is this one? Do we have any choices? Do we? All right. Yeah, final check, whatever. All right. Next one. Choose a graph. Next. Oh, now we get harder. Okay, actually, I would want to do one more just to kind of cement this. Okay. What if we have something like 3x plus 2y plus 6z is equal to 6? How would we graph it? Well, what we're going to do is we're going to set y and z equal to 0. Okay, so we have 3x is equal to 6, x equals 2. Okay. Set x and z equal to 0. So we have 2y is equal to 6, y equals 3. And then last one is set x and y equal to 0. And we have 6z is equal to 6, z is equal to 1. And we go off to graph this thing. Okay. Here's my x, here's my y, here's my z, x being 1, 2, so we would have that, okay? And then y would be, what is it, equals 6, y equals 3. What am I doing? 1, 2, 3, okay? And then z equals 1. So we'd have this sort of a triangular type of thing here. Most of them are going to look like this. And if you think about, like, if you leaned up like some kind of a wedge like this into the corner, that's what your plane would look like. All right. And again, it goes in all directions. Okay. But you've got this thing leaned up against the corner like this. Okay. And that's what our plane is going to look like. All right. So that's what we have. And we're going to pretty much use the same idea for all of these. Okay. They really are. So when I've got graph the level curves in a plane in the first quadrant of the xy plane for the following functions at the heights of z equals 0, 1, and 2. Okay. So it's not quite method of intercepts because intercepts say set them equal to 0, but we are definitely like setting a value for our x and our, or for our z rather. And there we have it. All right. In this case, I kind of want to do a little bit of massaging on this thing and say something like z is equal to y minus 3x squared. Okay, because who needs all the negatives? Okay, so we're going to have z equals 0. So when z equals 0, y minus 3x squared. So our function, our graph is going to look like y equals 3x squared. You guys could graph that. We know what that looks like. Okay, how about when z is equal to 1? So we have 1 is equal to y minus 3x squared. Go ahead and add to the other side. We get y is equal to 3x squared plus 1. Okay, that's when z is equal to 1. All right, and then we have 2 is equal to y minus 3x squared. Put this on the other side, we get y is equal to 3x squared plus 2, and that's when z is equal to 2. Okay, so when I go to start graphing this thing, and by the way, this does take some practice. Okay, I'm not going to be good at it right here because I have not had practice in a while. So we have our x, our y, and our z. But I tell my pre-calc class all the time, like, look, if you can graph as well as I can, if you can draw this thing as well as I can, and my ability is probably like about a fourth grader as far as drawing goes, you're doing fine. So don't be on yourself too much for I can't do this. Okay. What does the graph of y equals z squared look like? Well, what if I just graphed it this way? Right, here's my x and my y. What's this graph look like? It looks like that, doesn't it? How about when x squared, y equals x squared plus 1? What does that look like? Right, my y is my x. No, I'm sorry. Here's my y. Here's my x. Right, it's a parabola with a shift of 1. So we're just going to something like that. Okay, don't worry about being too precise about it, but there we go. And this graph. 2. Okay. Here's my x, here's my y. Right? So let's see if we can kind of translate this by looking sideways. All right. So it looks like we're going to do something like this, right? Y is equal to, We're doing this way, something like that. And then we're going to be going up to 1, so it's going to be like one of those models that get like you know, like a little stand on it. Okay, and then we just go up one more. All right, and that looks terrible, but that's the kind of thing we're trying to look at. Okay, so in the first quadrant, okay, I guess that's what they want. First quadrant, X, Y, Z. So here, and then here, and then here. Okay, as we are kind of going up. Okay, so I know this is a terrible thing to look at, but it's kind of like a what does this look like? It looked like kind of like a wider and wider hole as we're going up here. Okay, so I like this one. I like this one. Let's see, which one do I like more? I kind of like this one more because you can kind of see how the Y is getting further and further away from the origin. So this is the one I'm going to pick the best. You're going to have to graph a plane. I have never asked people to graph this because I've tried to grade these before, and they're terrible. Okay, but I'm not kidding when you guys. So when I say like you need some practice drawing this stuff, not everybody can do it well. But guess what? That's how we're going to do this. All right, discuss how a function of 3 variables of the form x, y, z might be graphed. Yeah, we have x, y, and z axis. That's what we've got. Okay, we don't need a 4th axis. I think we're okay. Okay, because look here, f of x, y. Would this count as an f of x, y? Right? We could have like a 3x minus 6y is equal to 10. Right? That's, we'd still have a z-axis going on here, right? It would look like a plane, but that would be okay. Okay, so that's a 3-dimensional thing. So yeah, I think we're going to be okay with that. Yeah. Oh, W equals. W equals. I didn't see the W equals. Yeah, I might choose this one. And I would not want to draw it in 2 dimensions. We could say in 3 dimensions, though. That looks delightful. I think we could check that. All right. I didn't see the W equals. All right. These are actually I actually rather like these problems. I don't like to quiz over these problems, but I do like them. If you had a decent high school math program, you learned about something called conic sections. All right, and conic sections, they're cones. Right? This is what the Greeks said a cone was. And since we're coming from the Greeks, conic sections, that's what our cone is going to look like. And if we took different slices, right? If I took a slice of the cone right across, what would the cross section be? Cross section would look like a circle. So we have x squared plus y squared is equal to r squared. That's a circle. What if I cut the cone like diagonally like this? Right? We'd have an elongated circle. So the way we say that is we have x squared over an a squared plus a y squared over a b squared is equal to 1. Okay, and that's our ellipse. Okay. Okay, so ellipse, right? Elongated, stretched out circle, one way or the other. Okay, that's terrible. Okay, if we only cut the cone in one spot, right, and we do something like this, we say, instead of making an elongated cone, we just cut it that way. What we're going to have, cross-sectional area, is a parabola. We're going to have y squared or y equals some kind of an x squared. Okay. So that's parabola, either up or down, doesn't matter. Okay, in this case, it would be down. And then one of them is we cut it directly vertically, right? So we'd have parabolas this way. Well, that looks like x squared over a squared minus y squared over b squared is equal to 1. Okay, that's a hyperbola. And we end up with something that looks like this and that. So these have analogies into 3 dimensions as well. Okay. First off, which one of these does not have a y squared and an x squared? Right? It's a parabola. So anytime you have like a one variable, say a variable just to the 1 power, there's going to be some kind of a parabolic issue going on. Okay. Then everything else has squares in it. What if there's a plus, right? There's an x squared plus y squared plus z squared kind of a thing. Well, are they the same coefficient? Like an ellipse, they're not the same coefficient. They're different. One variable has more weight than the other, so it's elongated. Okay. If they're all the same, then we got a circle because they're all the same weight. So that would be a sphere. Okay. If we have different weights, then we have something that looks like a football. Okay. And for hyperbola stuff, this one gets a little bit harder to see, but you know that if there's a minus sign between the 2 variables, then you've got some kind of hyperbolic thing going on. Okay, so I'm not going to ask you, we're not memorizing these. Okay, so if you're worried about like trying to memorize all these shapes, please stop. I'm not going to ask you to memorize the damn shapes, right? But it will go a long way of helping you. Like if you ever have to look at this stuff, it will go a long way of kind of visualizing what's going on. And quite honestly, these conic sections have served me really, really well when I've had the unpleasant task of like, visualize this shape. No, I can't. Okay, and I really can't. I have a very tough time visualizing the shapes. So if you're looking at this like I can't do this, that's okay. Let's just see if we can piece this together. Do the variables have all squareds? No, one of them's a 1. So there's some kind of parabola going on here. Okay, cones are going to have like there's going to be 2 linear parts to it. It's a circle, so there's going to be some squares going on, but cones don't look like, we don't have cones like this. It's going to look more like a bowl, and then we have they're not all squared, so it can't be this one. Okay, so we're stuck with some kind of a bowl shaped thing. Notice the negative signs are facing downwards. That's how we're doing this. Okay, so that's how we're going to check. All right, and I'm not going to promise you I'm going to get these all right, because I'm not. This one, x squared, y squared, z squared. Okay, they're all squared. There's pluses in between them. Great, so we're talking about a sphere or some kind of a football looking type thing. Do they all have the same weight? Like, no. The x squared is not divided by as much as like the y squared, which is divided differently than the z squared. So each of the things are going to have a different weight. They're going to be like an elongated sphere. You're going to stretch it out. So it's going to look more like a football than a sphere. Well, the only choice we have here is that one. Okay. So that's how we're checking that. All right. You just keep wanting to go. All right. All right. We'll come back to that. Okay. I just want to make sure. All right. There we go. Oh, this is a nice one. Fraud number. That's the, we're trying to figure out the size of the femur, right, from the, or we're trying to figure out from the femurs, from the different like constructions, like how big is the pace. So if you wanted to like animate a dinosaur, like how would you do that? And we could say, well, they're roughly this long, right? Here's our leg length, okay? And then could we make like how big would this animal be? And we could use this thing to figure that out. Okay, how fast does it move? We can't clock dinosaurs right around the track. It's not going to work. But we could get a rough idea of like how fast it moves by using this number, by comparing them to modern day. So what are we doing? We have G, we have let's just go through it. All right. So we have F equals V squared over GL. Okay, so F is equal to V squared over GL. Now, what did they say the variables were? G is constant, so we're on this planet, so that's 9.81. All right, and then V is the animal's velocity. V is velocity, so that's how fast it moves. Okay, and L is the animal's length. L is leg length. Okay, we can get that from a fossil, that's okay. And F, what is F? Different size animals, Freud number, F is, okay, L is the animal's leg length. Okay. I guess that F is the size of the, tell us what F is. Okay, animals change from a trot to a gallop at the Freud number is equal to, I'm sorry, I'm pronouncing that terribly. Hold on for a moment. All right, I think that handled it. So different animals change from a trot to a gallop at the same Freud number of approximately 2.56. Find the velocity at which this change occurs for an animal with a leg length of 0.24 meters. Okay, this is what we're going to do. We have the equation written down. What are we trying to solve for? We're trying to find the velocity. So we're going to say that V squared is equal to, right, F times G times L. All right. So really what we're looking for is V is equal to the square root. We're going to assume the positive one because always, it would make no sense to have like a negative velocity here. So we're not going to worry about that. Things we don't really run backwards. I guess we could, but we're generally not going to see that. All right, and now let's just plug in our values. Okay, so let's see here. We have 2.56 times 9.81 times L would be 0.24 square root, and this is equal to our V. All right. Just to tell you, I'm not sure exactly what this Freud number is, but since we have meters per second, animal's leg is going to be in meters. I don't think they're trying to mess with us about coming up with different units that we have to change. Okay. So 2.56 times 9.81 times 0.24. So we have the square root of, what was our answer here? 6.027, etc. And what we're going to do is we're going to take our square root button, and then I'm going to put in the answer I just got. Okay. And we get 2.45, 2.46 per second. That's our velocity. Okay. So let's see here. We'll go off and say, so we'll make 2.46. How we round to the nearest tenth as needed. Okay. So in this case, we'll say 2.5. Very nice. Okay. And then we can go the other way around. Say the animal footprints were roughly 1.5 meters in diameter. Okay. That corresponds to a leg length of approximately 6 meters. Okay, so let's go ahead by comparing the stride divided by the leg length of various creatures. Freud number is approximately 0.025. How fast was it moving? Okay, so they've done all the heavy lifting on this. We actually don't need this number, nor do we need this number. Oh, actually we do. No? Leg length, we did need the leg length. Okay, so we'll go from there. Okay, and again, they want to know how fast was it traveling. So we're still going to keep our V is equal to the square root F times G times L. Okay, let's assume gravity is constant, even for dinosaurs. So Freud number was 0.25. So this is 0.025 times 9.81. We'll assume that didn't change. And then L is going to be 6. And we're going to square root this thing. That's our velocity. I'm not good at knowing what speeds are in meters per second. So if you want to convert, that's okay. So let's go and have a look, see at this. So let's see, we have 0.025, okay, times 9.81 times 6. Pretty tall. We got 1.4715. Square rooted. Okay. Second function there, second function answer. And we got 1.21 meters per second. Or 1.2 meters per second when we end up rounding. Here's 10th. Okay. Great. Next question is the same kind of a thing where actually it's a little bit easier, where it's like, what's the expected number of gear and vehicle interactions? And we could go through and do some of this. Okay, but I'll let you guys do it. I'll go back to one of the other questions that I looked at and said, can't believe they asked you that. This one. Okay, for the function, f of x plus h, comma y, minus f of x of h over h is equal to. All right, so what are we supposed to do here? Let's go through it. We're going to be okay here. So this is 5y squared. Okay, plus 9y squared. So this is f of x h is equal to 5x squared plus 9y squared. And you want to know, what's this? All right, look familiar? Remember definition of derivatives and average rates of change from ages ago, calculus 1 and algebra. Okay, now we get to do it in multiple dimensions. That's what's going to happen here. Okay, so we have f of x plus h squared plus 9y squared. The only thing that has the h on it is the x part. Okay, minus, and then here we have 5y squared plus 9y squared, all divided by h. All right, so let's see what we can do with this. So this is 5x squared plus 2xh plus h squared. All I did was multiply this out. I can do this a little bit quickly. Xh plus h squared, okay, plus 9y squared minus 5x squared. Don't forget to multiply this through by both of them, minus 9y squared, okay. So there we go. Okay, I'm kind of interested to see where this is going to go. 5x squared plus 10xh plus 5h squared plus 9y squared minus 5x squared minus 9y squared, all divided by h. Some stuff cancels. Okay, there's some stuff that cancels. The 5x cancels, the 5x squared cancels, the 9y squareds cancel. So all we're left with, okay, this is going to be a pretty consistent type of an idea here. We have xh plus 5h squared all over h. There's an h that's constant. So we have h 10x plus 5h all over h. Some stuff cancels. Right? These cancel. And we just get 5x plus 5h. I'm sorry, 10x. Sorry, 10x plus 5h. So we're going to write that down as our answer. I'm going to see where this goes. All right, so we have 10x plus 5h. Okay. Let's see what we got so far here. All right, great. Now we're going to do it for y. Okay, that's fine. So here we go. We have f of x, y plus h minus f of xy all over h. All right, so we have, sorry for the length here. So we have 5x squared plus 9 y plus h squared minus 5x squared minus 9y squared all over h. Oops, it's a plus, isn't it? All right, 5x squared. This bit here, this is y squared plus 2 hy plus y squared. I'm sorry, plus h squared. Okay, so this is plus 9. Here we have y squared plus 2 hy's, okay, plus h squared minus, and I'll leave this in parentheses for now. Okay, all over h. Okay, 5x squared plus 9y squared, okay, plus 18hy's plus 9h squared minus 5x squared. Don't forget to distribute the negative sign of both of these, something I'm likely to forget to do. So h, some stuff cancels. Right, so you can see the cancels, this cancels. And what are we left with? We're left with 18 hy's. So we have 18 hy plus 9h squared divided by h. Okay, so we have 18y plus 9h. There's a y here, there's an h here rather, divided by h. Okay, why I do it that way? Just so that I make sure that I'm canceling and factoring correctly out of both terms. So our answer here is 18y plus 9h. Right. Let's see what we got. We have 18y plus 9h. Yep. Now, as h goes to 0, right, because we already have this result, as h goes to 0, so they're stringing us along with the derivative. We just get 10x, right? Because the limit as h goes to 0. This we can just do direct substitution. 5 times 0 is 0, so we're just left with 10x. All right. So now they want us to do it with y, so we have our 9h, right? What's going on there? That's going to 0. So we end up with, there we go, our limit. Oh, that's all they wanted. Oh. Here's the observation I want you to make. What happened to the rag when we'll use this one because we're here. As we took the limit, right, that went to 0. What happened to the terms with just x's in them? They canceled out, they went away. So when we take a derivative with respect to just the y here, x had nothing to say about it. Okay, so we don't have to take a derivative with like x and y at the same time. We take derivatives with x, we take derivatives with the y's. We don't mix and match. Okay, we will a little bit, but the mixing and matching will happen one at a time. So once you've taken a derivative with x and it's gone, right, there's no more x things that are happening. All right, so that's what's going to be happening next in the next section. All right, because we're going to learn how to take derivatives in multiple dimensions. That is actually, this is one of the easier things in the whole class. Okay, so don't look at this like we're going to be, don't put your mind like trying to go with like taking multiple derivatives or derivatives with functions that are going x's and y's. Like humans aren't good at that. So we just do one at a time. Okay, that's what we're good at. So don't look at this like it's going to be the worst thing ever. Trust me, that's coming. All right, so we're going to be okay here. All right, I'm going to let you go with that because I've been here for I think 40 minutes. So we'll stop, and hopefully that'll give you enough to kind of do this homework and walk through it and be okay. All right, so thank you, and I will see you tomorrow.